bienvenidos a todos a un nuevo, a ver qué largas. ¿Sí? ¿Ya está? Bueno, bienvenidos a un nuevo coloquio. Hoy tenemos la visita de Tomek Bulik, habla un poco español.
Sí.
Así que, bueno, Adrián va a hacer su presentación, va a decir algunas palabras acerca de Tomek.
Sí, digamos, entiende mejor español que yo inglés, así que no hay ningún problema. Él hizo su doctorado en Penn State University en Estados Unidos, después hizo un postdoc en la Universidad de Chicago, volvió a Polonia y estuvo en el Instituto Copernicano, o algo así,
Sí.
Que depende de la Academia de Ciencias de Polonia, y finalmente está trabajando en la Universidad de Varsovia como profesor. Desde ahí trabaja en proyectos como GES, que es de astronomía gamma en Namibia, CTA, que es el Cherenkov Telescope Array, que todavía se está construyendo, lo estuve ahí también. Y ahora también en proyectos nuevos como el Einstein Underground, algo así,
Einstein
para detectar
Telescope.
ondas gravitacionales en Europa, que me acabo de enterar que es un observatorio que va a estar a 10 kilómetros de profundidad enterrado. Y también en Virgo, que es la versión europea de LIGO, digamos. Así que bueno, nos va a hablar sobre el origen gravitacional de ondas gravitacionales. Le agradecemos mucho que esté aquí.
Okay, so thank you very much for having me here. And it is my, I don't know, already 10th visit to Argentina, but it's the first time I'm here, and I'm very happy that I finally came to the institute. So I'm going to talk about the origin of gravitational wave sources. So the plan for today is to outline the gravitational wave detections, what are the measured properties of the sources that we can find out in gravitational waves, and find what are the source properties, what are the measured properties that we really see. Then I'll talk about models and their predictions. So what are the possibilities of making these sources in the astrophysical context, and I'll try to compare the models and the data and decide what, and let you decide what is what are the best models, what are and how can we distinguish them in the future. So I understand that you all know about the LIGO and VIRGO collaboration, and that there are these very nice instruments. On the left-hand side you see LIGO, Hanford and Washington, and VIRGO near Pisa. These are 4 kilometers interferometers. This is a 3 kilometer interferometer. And they work together, they analyze the data together. It's an example where everybody realized that competition makes no sense, just collaboration is the only way to go forward. They have been working for a long time. There were 3 observational runs. There will be a 4th one coming up this January. And what have these experiments been observing? So that's the detection of the first ever source of gravitational waves, which was found by the LIGO detectors. So you see the signal, and you see the overlaid on this the predicted signal that will, modeled signal for this source. So the point was that in 2 detectors at almost the same time, we saw significant signals, and these signals were coherent. So the signal in one detector was the same as in the other detector, and the detectors are 3,000 kilometers away. The time difference between the signals was 6 milliseconds, so it was less than the travel time between these 2 observatories, which is what we expect if the source. Now it would be 10 milliseconds if the source was along the line that connects these 2 sources, but if it's somewhere else in the sky, then this delay is shorter, and from the delay we can get some information of the position in the sky. And the nature of this signal points out to an inspiring source, because you see that the amplitude is rising and the frequency is rising. And for a typical mechanical system that we put out of equilibrium, if you take a bell or whatever, then you have the constant frequency and decreasing amplitude. For gravitational wave bound signals, if you take away energy from two sources, they come closer, they interact more intensely, and the typical time scale shortens because the orbit shortens. So that's what we expect, and that's the signal. So so what can we measure from this type of signals? We can measure these parameters. I'll explain what they are. One is the so-called chirp mass. That's a combination of the two masses of the inspiring objects. And the point is that the rate of change of the frequency of the system and the amplitude of the signal are only described by this parameter. So this is something that can be measured directly from the waveform, and it also tells us about the expected amplitude. So given this and some information on the location in the sky, we can get the distance to the source. So if we see so this comes from the inspiral part of the signal. If we see also the ring down part, once a new black hole is formed and it relaxes to a Kerr configuration, we can get the total mass, and from the spiral part we can get the mass ratio, but with much worse, much larger error than the chirp mass. Then there is a quantity which is called effective spin and effective precession spin that I will describe in a moment, and we have the statistical properties. Once we see many sources, we can show distributions of the observed parameters. The effective spin, what is the effective spin? So you probably know that for black holes the spin can be between 0 and 1, and that there is a maximum value of the spin. And if we have a binary system, that's the orbital angular momentum. This is the spin of one black hole, this is the spin of the other black hole. Then the effective spin is defined by this, and it's effectively a mass-weighted projection of the spin of the individual spins onto the direction of the angular momentum of the system. So if these two spins are aligned, the effective spin will be 1, and if they are aligned and maximal, then the effective spin will be 1. If they are anti-aligned, the effective spin will be -1, and if it's small, that can mean that the spins are pointing in the orbital plane, or that they are small, or that they are opposite. So then there is a little bit of ambiguity what they are, but here we are with this quantity. And this can be measured pretty well. However, there is another quantity which is effective precession spin, which is related to the perpendicular components of the spins, given by the formula below that you probably don't see here very well. But this quantity cannot be measured very accurately. This is also between 0 and 1, and effectively you can get it with the errors of like 0.5, 0.6. So there is not a lot of information that we can get from the current measurements of this quantity with the quality with which we measure the waveforms of the binaries. So then there comes the plot with masses, and maybe you have already seen this. This is the plot that shows the masses in black holes. It also suggests that they are stellar masses. I'll talk about this. So here is the mass scale. These objects are electromagnetically found objects. The yellow are neutron stars, the red are electromagnetically found black holes, and the blue ones are black holes that come from the LIGO VIRGO measurements. The orange ones are neutron stars, or neutron stars, black holes. We don't know really what they are, so they are in two colors here. So one thing that is immediately you can notice is that the electromagnetic black holes sit here, while typically the gravitational wave black holes sit a little bit upper in the mass spectrum. And there are people who say that, okay, so this must be different populations because the masses are different. And I don't agree with this, because there is a lot of selection effects that lets us see more massive black holes in gravitational waves much easier. And I think that these two populations that we see here are actually one population that is seen from two different angles. And one most important selection effect is that the signal to noise in gravitational waves is almost proportional to the mass, to the chirp mass, in the power of 5/6, so practically linear. It goes linearly with mass. So the distance to which we see these binaries scales as mass, and therefore the volume scales as mass to the third. So if there is it's much easier to see the more massive ones. From here to here, the mass goes 5 times up, so the volume goes 5 to the third up. So even if there is a smaller density in the universe of these massive objects, we can still see a lot of them because we see them farther away. They are much more bright. They're much brighter. But there is one more thing here, is that we see these objects up to the mass of about some of these component masses reach 80 solar masses, and that's important. 80 solar masses is a lot. So I'll now flash some of the plots that show the detections. So here we have the detections from the O2 and O3 runs. This is the total mass versus the mass ratio. These plots are elongated because a better defined parameter is the chirp mass that I'm not showing here, but typically for these systems, the chirp mass is constant along this banana-shaped regions. For the higher masses, a better determined parameter is the total mass, and that's why this shapes become more round as we go to the higher mass range. So we see them up to high masses and high total masses, and we see some of this region are binary neutron stars. This region are mixed binaries, and this is binary black holes. So most of the sources that we see are binary black holes. And then, let's think about the distribution of masses. So this is the distribution of masses that is modeled for all about the 100 sources that we see. So this is the mass of the more massive component of the object, and there are several mass models. So you have 100 points, and you try to fit a distribution to that. So you have to model it with something. So one thing is that a model that allows a few peaks fits this distribution much better. So the distribution of masses that we see is not like a power law or exponential. There is some structure in it. And when I started working also in high energy gamma ray astronomy, there was a saying that if you see one photon, it's a detection. If you see 2 photons, it's a spectrum. And if you see 3 photons, it's a spectral line. So we are here, mathematically the problem is similar, because we have about 100 detections, and we start to see spectral lines in the distribution. So they are not very certain, but at least they fit better than just a straight line. So that's what we know, that there is a structure in the mass spectrum. Now, for the spins, this is the chirp mass, and this is the effective spin. That is this mass-weighted average of spin. So you see that most of these effective spins are consistent with zero. There are some cases that are off, this one and this one, but typically these values are relatively small, below 0.5, and that they can be, and they are, and only for larger masses maybe they are a little bit off. So it's important to also, and this is for the spin and chirp mass for the for the third catalog, which shows the same structure, and some of them are very badly determined. But from these plots, you don't see very well the statistics of this of the effective spin. But here, if we plot together add together the probability distributions for the effective spins, this is what you get. And the point is that the centroid is slightly to the positive value. Yes? So there is there is a little bit of evidence that on the average, statistically, effective spins tend to be positive, which means that the spins like to be a little bit aligned with the angular momentum, or maybe they are small and aligned, that they are not maximal, but there is a little bit of trend to the positive values. But there are examples where they are definitely negative. So it's a statistical statement. It's not like every object is like that, but this is what they are. And also this is the precession spin, and the precession spin is of the order of 0.02, and these two information tell us that the typical spins of these black holes should not be maximal, because if they were maximal, then this distribution would go to higher values. So most likely the spins are slightly aligned and essentially small, not close to the maximum value for the spins. Now let's look at the rate versus the redshift. We can calculate the rate density, which is the number of gravitational wave bursts per unit volume, per unit time, and the units that are now used is per gigaparsec cube per year. And we can try to find whether there is a trend with the distance from us or with the redshift. And there is a definite tendency that the rate goes up. And in order to guide your eye, there is this dashed line here, which with the arbitrary normalization shows the shape of the star formation rate history. So at least up to this point where we can do it, where we can measure it, the gravitational wave rate density has about the same dependence on the redshift or distance as the star formation rate history, which is an indication that we have something that connects us with the stars. Okay, so that's the overview of the observations, and now let me go into how to make these things in an astrophysical situation, how to, what kind of mechanism we can invoke to produce them. So what are the challenges to form these things? So first of all, we have the black hole masses, which reach up to 80 solar masses. Here the problem is that if you take standard stellar evolution, there is the process of pair instability supernova that leads to distraction of stars that have cores more heavier than 65 solar masses. So in standard stellar evolution models, you can't make black holes with stellar evolution that are heavier than 65 solar masses. And of course, as usual with stellar models, you can twist and stretch the models and push it up to 80 solar masses. But the more you push it, the more difficult it gets and the more unlikely it gets. So that's a problem. Then spins. I've tried to convince you that the spins are low, but the spins in black holes that we see electromagnetically in binaries with stars are typically close to the maximum value. So this is a challenge. Then orbital separation. In order for a black hole binary to merge, it has to start within the Hubble time. It has to start with a period of not more than 2-3 days. And the size of the orbit of a system like that is certainly much smaller than the size of the stars that should have produced these black holes. So we have to find a mechanism to produce the black holes and bring them together in order for them to merge, and so that we can see them, because they have to. If they come from stars, we have to put them closer, because otherwise it's not going to work. Then there is the rate, and I will try to convince you that there is quite a lot of them. So the number that we see is quite high. So that also leads to constraints on how to make them. I'll just argue that we cannot look for very exotic environments. We have to look for something that is more standard in the universe than typical. So, what are the options? One are stellar models, and one is the binary evolution in the field, or there's an option of it called chemically homogeneous model, where the stars rotate quickly and don't expand their radii. Then there is the cluster evolution, so including the nuclear clusters, and globular clusters. The point is that apart from just the binary evolution, you can have collisions between systems, and you can exchange partners. So you can have a black hole with a star, another system, or a single black hole. They will collide. There will be a little bit of interaction, and then you make a black hole out of two black holes, two systems that evolved separately. There is an AGN disk model, which is in a way an analogy to planetary disk, where you bring in particles together by interaction with the gas in the disk, and that's why you make planetoids. And here in an AGN disk, instead of particles, you have black holes, and you bring them together and make merging black holes. And of course, then there are the primordial black holes, where you do not invoke any stellar evolution, but you make them in the early universe and then make them into binaries. So I'll now give a little bit of overview of every one of these. So isolated binary evolution. Masses must come from stellar evolution, but there is this per instability supernova maximum. So there is a little bit of trouble with this model, because we see component masses of 80 solar masses, which are on the edge of what we can produce with just the stellar evolution. And effective spins, because now in this evolution we have mass transfers between the objects, and when there is mass transfer, we also transfer angular momentum, and the angular momentum may lead to the fact that the effective spins will change and will be aligned with the angular momentum of the system. So that means that effective spins should be at least partially aligned. And the question is small or large, and that's I'll go into. I'll talk about this in a moment. Rates should follow the star formation rate, so that looks pretty good. I mean, I could describe this scenario for you, but maybe if later if there is more time. Now, in the cluster evolution, masses can be much larger, because we can have hierarchical mergers. We can have a merger of two black holes, then we have a black hole with larger mass, and then this black hole can merge again, so we can have mergers of black holes with the masses above the per instability supernova limit. Now spins, when we make binary black holes by collisions of systems, should be not aligned and should be random. So the average of the spin should be 0, and that it can be, the problem is that if we have these hierarchical mergers, then after the black hole that forms in a merger of two black holes gets the spin of about 0.7, because that gets the orbital spin of the two systems in, and it ends up to be a fiducial value around 0.7. So this in the hierarchical mergers, one of the spins should be large and not aligned. I mean random. And rates, there is a little bit of discussion what the globular clusters formation rate history was. It should probably peak at higher redshift than the star formation rate history, but we don't reach that far away with our instrument. For the AGN disk model, this is the story. We have the stellar black holes. It's similar in a way to the model of the stellar evolution, so there is this limit on the mass, but then we have the model similar to the planet formation scenario. Then the merger should take place in the disk, spin should be isotropic, but rate should be small, and I'll argue why that should be in a moment. Okay, and then primordial binaries. This is where we get the most uncertain predictions, because first of all, masses should correspond to some phase transitions in the early universe. And because these are phase transitions, we also expect that there should be some structure in the mass spectrum of these systems. Because a phase transition corresponds to a certain age of the universe and certain mass scale, so we could be making black holes with specific masses more likely than others. So there is some, we know that there is some structure in the mass spectrum, but then spins should be random and small, because it's difficult enough to make a black hole in the early universe, but make it quickly spinning is even more difficult, because you essentially collapse something under a horizon at a given time of the universe. And the rates do not have to follow the star formation rate, because this is completely unrelated. Yeah? So comparison with observations, and now let me go to my argument about the rates. So the observed values for binary black hole mergers is in this range, 17 to 45 gigaparsec per gigaparsec cube per year. Then for binary neutron stars, the error bars are much smaller, and for mixed binaries, the error bars are close to the binary neutron stars. And when we have a number like this, we want to know whether it's big, small, what to compare it to, right? So here is my short back of the envelope estimate. If you take the local supernova rate, we know that there is about one supernova per galaxy, like our Milky Way, per 100 years, more or less. Then the density of galaxies is about one galaxy per 100 megaparsec cube. So if we take a gigaparsec cube, there should be about 10 to the 7 galaxies in a gigaparsec cube, and we have one supernova per 100 years, then the local rate of supernova in this unit is about 10 to the 5 per gigaparsec cube per year. Now we have something to compare with, which is this value, 17 to 45. Okay, and then this is the local supernova rate is roughly the rate of formation of neutron stars in the local universe. We make 10 to the 5 neutron stars in a gigaparsec cube per year. The rate of formation of black holes, because they come from higher masses, stars, is about 10 times lower, so it's about 10 to the 4 per gigaparsec cube per year. And this is a number that we can compare with that one. So we know that 1 in about 100 of black holes that are found in the local universe end up in the merging black hole binaries, right? And similarly for neutron stars, 1 in about 100 to 1,000 is ends up in a merging binary. And I think that this is quite a lot, because you have to keep them in a binary, and you have to only take the population that manages to merge in the Hubble time. And also it means that if you take a cosmic environment that in which there is less than 1% of the mass of the stellar mass in the universe, it's very difficult for this environment to be used to make these objects. It has to be something that, some cosmic environment that encompasses quite a lot of the stellar masses. So now the rates, we can, how do we calculate the rates? We can use a parameter which I call the binary black hole production efficiency, which is the number of merging black holes per unit mass. So if you have some cosmic environment, you put some stellar mass, you see how many binary black holes you make out of it, and that's the definition. Then you have some delay times between the production and the merger, and the mass distribution, and then you can calculate the rate density local and as a function of the redshift. So for the binary model and for the globular clusters, the point is that if you put the total star formation rate in solar masses per megaparsec cube per year as a function of the cosmic age, the red line corresponds to population 1 and 2, so typical stars like we see. This is population 3, the first metal-free stars, and this is more or less an estimate of the star formation rate in the globular clusters. So the total mass in population 1 and 2 stars has been much larger than the ones in globular clusters, but in globular clusters, this binary black hole formation efficiency can be larger than in the field, in single binary evolution, because apart from just binary evolution, you have the possibility to exchange partners in collisions, and therefore the paths to make binary black holes are more abundant. So the basic arguments about the rates is that the formation scenario must be kind of generic. It has to include a generic cosmic environment, and exceptional environments, something that is not very often encountered, must produce binary black holes with much higher efficiency to explain the rate. So dense stellar regions, I think, are not favored, but they do contribute, and I'm very skeptical about the exotic models like the AGN model, because the fraction of the stellar matter that is in the AGN disks in the universe is about 10 to minus 4, 10 to minus 5 of all the stellar matter. So in order to make up for the fact that there is so little matter, you would have to make them with extremely high efficiency, and there is that even if you make it with 100% efficiency, you will not make up for the fact that these environments are so exotic and rare in the universe. Now, for the binary evolution, we see too heavy black holes, so this is a problem. because we see black holes with the mass above 65 solar masses. Spins are slightly positive, but they are small. And are these small spins a problem? I'll just argue in the next slide. And the rates are consistent with the star formation rate history. Of course, we expect some delays, but we expect that there will be a correlation between the star formation rate history and the merger rate density. Now, about small spins. So, black hole spins in accreting systems that are found electromagnetically are large. These spins are smaller. So what's the point? First of all, I think that there are lots of selection effects that in the accreting binaries, there is, especially in the low mass X-ray binaries, the time for transferring the mass is very long, and you can transfer quite a large amount of angular momentum to a black hole. But if you look at the young pulsars, young neutron stars that are formed in supernova explosions, then there are statistical arguments that the typical periods of young pulsars are between 30 and 100 milliseconds. 30 to 100 milliseconds for a neutron star is a very slow rotation rate from the relativistic point of view. So in supernova that make neutron stars, we typically make neutron stars that are slowly rotating. Then this is an argument that maybe in most of the collapses where we make black holes, the typical spin values are also low, because I mean this is not a proof, but this is perhaps an analogy that tells you that it's not such uncommon to have low spins in black holes that form in stellar evolution. Then there is the second argument that we know, or we believe, that long GRBs come from quickly rotating black holes that are formed inside collapsing stars, and then there is a GRB formed. But we know that the GRB rate is about 1/1000th of the supernova rate. Therefore, this quickly spinning black holes are probably very rare, because otherwise we would make almost every supernova, or not even supernova, core collapse that makes a black hole would lead to a GRB, and we would see the rate of GRB being about 1,000 times higher than we do. So I think that there are arguments that black holes in stellar evolution may typically be formed with small spins, and that this is not a big problem for the stellar evolution scenarios. For the cluster evolution, masses are fine because they extend above the per-instability supernova gap, and they can extend because we can have hierarchical mergers and we can bypass this limit. However, spins are on the average positive. For the cluster evolution, we expect that the average should be 0 and there would be some distribution. But there are some individual events with anti-aligned spins. So it is quite likely that what we see is some of a distribution of spins that is isotropic and some that is positive. But we cannot explain all the events with the cluster evolution just because of the spin argument. Now, the rates should increase and may follow star formation rate, because we don't really know the globular cluster star formation rate that well. And there might be a peak at the redshift of 2 or 3, but that's too far to see at this moment. The AGN model of formation. Here, one argument for this model is that in this event, 1905-21, there was a quasar flare after 35 days at the same location, and it was used as a as an argument that this for this particular model. In this model, there is also a possibility of forming eccentric binaries. Most of the binaries that we see have eccentricity very close to zero. However, I think that the rates are very low, in my opinion, because of the expected rates are very low because of this argument with the fraction of stellar matter in the galactic disks that is really 10 to minus 4, 10 to minus 5, all the matter, which means that I would expect 1 in 100 to 1 in 1,000 events to originate from this scenario. And people who talk about this scenario say, okay, we have seen 100 events, so one of them comes from this. So with this caveat, I'm fine with this model, but it's not something that can explain all the events, in my opinion. Now for the primordial, we have several problems. One is the distribution of masses, and there is, in the primordial scenario, you would also expect that there will be black holes with the masses below the neutron star maximum mass limit, or even minimum mass limit, because you can have also black holes that form the primordial with the mass of 1 solar mass or less. We don't see any such events, but on the other hand, the efficiency of seeing low mass objects is very low. Spins are spins are positive, and in this case we expect that the spins should be on the average 0, and we expect them to be small. So spins being small is fine, but the effective spins being positive is not fine for this model. Then we know that the rates follow star formation rate. And for this model, there is no connection between the star formation rate and the black hole formation rate. So, the fact that one rate follows another would be a conspiracy, would be something that two completely independent effects lead to the same observational consequence. So I think that I don't like the conspiracies, so I'm not very happy with this explanation. So now to sum it all up, then we have masses, spins, and rates. For the binary, I'm not happy with the masses. I'm happy with the spins and rates. So I give a yellow light here. Maybe we can stretch it a little bit higher, but maybe this should be a red light. For the cluster evolution, masses are fine because we can go to higher masses. Spins, I give a yellow light, don't give a red light, because we can have the distribution of spins that contains two components, the isotropic and and slightly positive. And the rates also can follow the star formation rate. And for the primordial, we don't see the low masses, but on the other hand, there is some structure in the mass spectrum, but the structure in the mass spectrum is also expected in the stellar models. Spins are positive, it should be 0, and the rates, there is, one is the conspiracy with the rate following the star formation rate, and another is the conspiracy with the level of the rate, which is consistent with star formation models, stellar models. And in this case, the rate could be much higher or much lower. So it's a different argument. Why does it really fall into this range? And it's not something else, but we don't have very good models of or predictions for how the primordial black holes are formed. And of course, there is still another problem. That primordial black holes are made single when one volume under a horizon collapses in the early universe, but then you have to make them double and bring them together, which I think is also something that is unsolved. So I'm not very happy with the primordial model, but I think that what we see is some mixture of this and this model that can lead to that just one model is not enough. We need two of them to explain the observed population of binary black holes. And for the what next, I have this slide that is slightly outdated if you look at this scale. We will have another. No, this was 01, 02, 03. I presented the results from all of that. Now we expect to start a new set of observations called 04 with Virgo and LIGO, and CAGRA is supposed to join. The CAGRA planned sensitivity has not reached this level. It's lower, but Virgo and LIGO should have this sensitivities by January, and we expect to see something like a binary black hole every 2-3 days for the next 2 years. So the number of objects will increase, and I think that we are going from the epoch where we were extremely excited by every new current object, and now we'll treat them as noise and just look for outliers or for statistical properties. So we are quickly transforming into the standard astronomy, where we have plenty of sources and look for the most interesting ones with these things. And some of the problems that I expect outlined, which can be solved by looking at higher redshifts, and further sources will be explained in maybe 15 or 20 years by these two upcoming experiments: the Einstein telescope, which is a planned underground observatory in Europe on an underground triangle with the size of 10 kilometers, or Cosmic Explorer, which is a US planned 40 kilometers interferometer, which should be able to see binary neutron stars to the redshift of 3 and black holes to the redshift of 20 or 30, where probably there aren't so many at all. And so there's some future in this field. So thank you very much.